Okay, so we have again come back to Lee's algebra exercises, and we have been going through cyclic groups. So let us see this next one. Here, G is a cyclic group with A as generator, A as one generator, and it's given that G is an infinite cyclic group. That is, the number of elements in G is infinite. And M and N are two positive integers. We then have to find a generator for this intersection. Now we know that the intersection of two subgroups is a subgroup, and this is the intersection of these two cyclic subgroups of G, generated by A to the power M and A to the power N respectively. And we know one more fact about cyclic groups is that any subgroup of a cyclic group is itself a cyclic group. So that means this will also be a cyclic group, and so that is why it makes sense to say that we want to find a generator for this. So let's see the solution. Let K be the LCM of M and N. Okay, so what we are now going to show is that A to the power K is a generator for this intersection. So let's see how that is possible. Then, because K is the LCM of M and N, so K is a common multiple of M and N. It is the least common multiple, but of course it's also a common multiple. So that means it is a multiple of M, and also it's a multiple of N for some integers alpha and beta. Okay. Now, if we look at this power, the kth power of A, then you can, of course, in place of K, you can write M alpha, and that equals, by one of the rules of exponents, that equals this. And from the look of it, you can immediately say that this belongs to the cyclic group generated by A to the power M, simply because it's an integral power of that generator. And at the same time, we can do the other calculation also. Instead of replacing K with M alpha, you can also write N beta, and similar arguments lead you to this. So this power of A belongs to the intersection of these two cyclic subgroups. Now, because A to the power K belongs to this, any integral power of A to the power K will also belong to this. In other words, the cyclic subgroup generated by A to the power K will be contained in this, which implies that the cyclic subgroup generated by A to the power K is contained in this. You may be hearing a little rumble outside because it's raining and there's thunder and lightning. It came suddenly out of nowhere, but it's okay, it will reduce the temperature a bit. Anyway, so now we have in fact achieved one half of what we want. We want to show that these two things are equal. So now we have to prove that the reverse inclusion is also true. So we consider any element here, then we have to prove that that element belongs to this set also. Now we haven't used x anywhere. Let x belong to this intersection. Then of course x belongs to both the sets, and that is why x will be equal to this a to the power m whole to the power gamma for some integer gamma, which is a to the power m gamma, and again by one of the rules of exponents, at the same time delta equal to n delta for some gamma and delta belonging to the set of integers. So we have, but they are equal, right, because both of them are equal to x. So we have this, or if we manipulate this equation a little bit, keeping in mind that we are in a group, m gamma minus n delta equal to the identity element in our group. We know what the identity element is, it's the 0th power of a, but you can just simply write identity because it's not going to play any role. I mean, you won't get anything new by writing a to the power 0. Okay, now you look at this equation. This equation of course is true if this exponent is equal to 0, but some other integer values of this exponent may also give you e. However, that cannot happen. Do you see why? Because, so what I am saying here is that if we have a non-zero integer here above a as the exponent for which this equation is true, then the problem is that that would imply a has finite order. But a is a generator of our original group G, and it's given that G is an infinite cyclic group, so that will be contradicted. If m gamma minus n delta is not equal to 0, then a is of finite order, which contradicts the hypothesis that this is infinite. But there is a little, I mean, still there is a little explanation that maybe I should provide. How am I concluding that if this is non-zero, then a is of finite order? Being non-zero means what? That it is either a positive integer or a negative integer. Say it's a positive integer. Say this is a positive integer. Then what does this equation tell us? It tells us that a positive integral power of a equals identity. So by the definition of order of an element in a group, a would then have finite order, and the least such positive exponent for which this equation is true would be the order of a. That is a contradiction. On the other hand, if this is negative, then from this equation you can write another equation which you get by taking inverse on both sides. Again by using the rules of exponent, this will be n delta minus m gamma, and E inverse of course is E, but then n delta minus m gamma is a positive integer. So again from here we conclude that A has finite order, which contradicts our hypothesis. So that's why at once we are writing from this itself that A is of finite order. When you see this kind of thing for the first time, it may be somewhat difficult to see how we can immediately write like this, but see, we are immediately writing like this means we have seen this argument, this part that we are suppressing here, not writing here once. We have seen this kind of thing once, and then we are just simply choosing to not write everything in detail. This kind of suppressing things you will find in many places, in proofs, in solutions, because you get used to these things. So things become more and more natural, and we tend to not write everything all the time. So what does this contradiction tell us? It tells us that this cannot be non-zero, it has to be equal to 0. So we must have m gamma minus n delta equal to 0, or m gamma equal to n delta. Okay, so m gamma should be equal to n delta. Let L be this common integer which is m gamma and also at the same time n delta. Okay, then let's go back to where these things are coming from. It is coming from here, right? So x would be what? X would then be a to the power L, where from the definition of L we see that L is a common multiple of m and n, because gamma and delta are integers. Where, so we are going to write that now in words, where L is a common multiple of m and n. And we write this because that makes us conclude something. The least common multiple of any two integers, when it exists, divides any other common multiple. So that means this L being a common multiple of m and n would be divisible by the least common multiple of m and n, that is k. L is a common multiple of m and n, and hence k divides L. Okay, k has to divide L, that is L is equal to K times, say let's write epsilon for some integer epsilon, but then x, which is a to the power L, is now a to the power k epsilon, and you can write this as the epsilonth power of a to the power k, again using the one of the rules of exponents once more. And the form of this element tells us that it belongs to the cyclic subgroup generated by a to the power k. So you recall where we started. We started by considering x to be any element in that intersection. So now we have managed to show that x belongs to this. So this intersection is also a subset of this. We thus have equality, i.e. a to the power k is a generator for our intersection, and that's what we were seeking. So now we are done. So now, in fact, if you encounter because this is an abstract one, right? Here an infinite cyclic group is given. Now if you encounter a concrete infinite cyclic group, for example the group of integers, there you can apply this result, and you would know when you consider such an intersection of two cyclic subgroups that you already, even before this solution or before this exercise itself, you knew that the intersection would be a cyclic group, but now you know one of its generators. Okay, so that is the solution. Next, this next one is purely number theoretic. Let n be a positive integer. Let n be a positive integer, and let capital T be the set of positive integers that divide n. That divide n. Show that we have to show something like this. Summation phi of k, where k varies over the set T, is equal to n, where phi of course is our familiar Euler's phi function, which calculates the for example, phi of k calculates the number of positive integers less than k and relatively prime to k when k is greater than 1, and additionally phi of 1 is defined to be 1. Now this is actually a result, a theorem, a standard theorem in elementary number theory, and in fact the solution that now I am going to write, it's a proof, it's a standard proof of that theorem, and you can find this proof in the book Elementary Number Theory by David M. Barton. It's a famous book, famous text on elementary number theory, and the proof is in fact that what I have found in that book. Now before we write the proof down, in fact that would be the solution, let us look at an example and try to understand what the strategy of the proof is in that example, and that example itself is also found at the end of the proof in that book itself. So okay, so let us first see what the exercise is saying. N is a positive integer and t is the set of positive integers that divide n, that is t is the set of all positive divisors of n. Then we have to find this, that is, if we take the sum of all the 5 values of the positive divisors of n, then we get n itself. So let's look at that example. Let us take this n equal to 10, say. Now what we are going to do, or what the author has done, or rather what Gauss did, because this is a result due to Carl Friedrich Gauss, is that we are going to divide all these integers in this set into classes. How? See, first you look at what t is for this particular n. T is the set of all positive divisors of n. So for this n, t consists of these 4 integers, because these are the only positive divisors of 10, which you can clearly see. You just factorize 10, you write its prime factorization, from that you can figure out. And because it's a square free integer, it's not divisible by the square of any prime, so it's rather easy to find the factors. Okay, so now what we do, we look at some sets which are defined like this, S1. So what S1 is this. S1 is the set of all elements n such that, well, perhaps I should also mention, just to be precise, that m is the positive integer such that m lies between 1 and n, and the greatest common divisor of, okay, why am I taking n? 10, because my n is 10. This is equal to 1, and this 1 is this one. Okay, if you have something else here, that would come here, and this suffix of course is this one. So that means for each element in T we are going to have one such set. Now you can perhaps understand what the other sets are going to be, but before we go to the other sets, let us just see what the elements in this set are. So that means here we are trying to look at And where is this m coming from? M of course is coming from this set, the set of first 10 positive integers. So we are looking for those integers that are less than or equal to 10 and relatively prime to 10, because the GCD should be 1. So let's see, 1, 2 is not an option, 3. The even integers are not options. But the odd integer 5 is also not an option, because 5 divides 10. 6, 7. 7 is an option. Then 8 is not an option, 9 is an option. And that's just it. Okay. So we have, okay, I think I should, maybe I should show all the things here so that you can see it more clearly. 4, 5, 6, 7, 8, 9, 10. So that means we have taken into account these things in this set. Next, let's look at S2. The definition of S2 is also like S1. The only difference is that here we would have 2. Okay, so now what are the possibilities for n? 2 of course is an option. The GCD of 4 and 10 is also 2. The GCD of 6 and 10 is also 2, because 6 is 2 times 3 and 10 is 2 times 5. 3 and 5 are relatively prime, so the GCD is 2. So that means 6 is also an option. And 8 is also an option, and that's just it. So in this second set we have covered 2, 4, 6 and 8. So we have considered 1, 2 and now 5. S5. You may be wondering why I am writing these things again and again, since we have already understood what these S sets are. The thing is that when we see something for the first time, it's better to write everything as many times as we can, so that it sticks here well. Next, we are looking at this type of M, and this is going to be what? 5 is an option, and that's just it. And there is only one more, S10. If S10 is just 10 itself, so you can see that these sets actually partition this set. If we call this set say S, then S is the union of these sets, and these sets you can clearly see by looking at the elements of these sets that these sets are mutually disjoint. That is, no two different sets from among these 4 sets have any intersection. I mean, their intersection is the empty set. Okay. So now, why is this strange thing, and why are we doing it? You will notice something. You see, the number of elements in S1 which I am writing like this because this notation is used for the order of a group, so we may as well use it to denote the number of elements in a set or its cardinality. I think it already denotes the cardinality because I am dealing with some other books also now, so I don't remember. Maybe this itself denotes the cardinality of S1. We know that this cardinality is 4. Now you note one thing, that this will only be an observation, an ad hoc observation, is that this 4 is in fact the phi value of 10, and you can in fact understand why it is the phi value of 10, because here we are considering particularly those type of n, right? However, it may not be so direct for S2. The cardinality of S2 is also 4, and here it is the, okay, let me write like this, it is the phi value of 5, because the phi function value of 5 is also 4, and that 5 you can interpret as 10 divided by 2. The cardinality of S3 is 1, which is the phi value of 2, because there is only one positive integer less than 2 and relatively prime. In fact, there is only one positive integer less than 2, and that turns out to be relatively prime to 2, which is 1. So that's why the phi value is 1 here, and this is equal to this. And finally, see, carelessness S10. Cardinality of S10 is also 1, which is phi of 1, and this is phi of 10 divided by 10. Okay. Now you can of course understand that because these 4 sets partition S, so the cardinality of S would be equal to the sum of these 4 numbers, the cardinalities of the individual sets. But what is the cardinality of S? Now that we have seen what these sets are and what they did, we can wrap this part off, and we actually do not need the exact elements that these sets have, but rather how many elements these sets have, each one of them has. That's what we need, and we have that now with us here. Now the thing is that the cardinality of S is 10, and because of the partition we have this. Four plus 4 plus 1 plus 1. Okay. Now this 4, of course, we have we have been able to see that this equals this. However, originally 4 is what? Phi of 10 plus this 4 is phi of 5. This one is phi of 2, and this one is phi of 1. So you can now clearly see that this is equal to the summation of the phi values of k as k varies over t. 1, k will take these values 1, 2, 5 and 10, and you get this. Okay, but so what do we see here? We see here a kind of strategy using which we can get a proof. However, some questions still remain. How is it that these cardinalities equal these 5 values? So that will now be answered. So now we will turn this observation into a proof and hence a solution to the exercise. So let us now start. Now if we look at the abstract proof or the solution, we will immediately understand what the, not what I am trying to say, because this is not my proof or my solution, but what the author tried to say here. So solution, I need if, give me a moment. Solution. In fact, this is how actually the proof starts in Barton's book. The integers between 1 and n can be divided into classes as follows. For each positive divisor d of n, that is, for each d belonging to t, like what we see there. This d can be 1 or 2 or 5 or 10 when n is 10. Okay, so for each positive divisor d of n, we define, of course, the set SD like this, such that there is in fact really no need to write m greater than or equal to 1, but anyway, let's just keep it like how we find it in that book. GCD of m and n is equal to d. Okay. Sometimes when we define sets like this, using your set builder technique, set builder method, we are worried that maybe the condition that we have set here in defining such a set will not be satisfied by anything, but that is not a problem. If no such element satisfies your given, not here but in general I am saying, if no element from your in this type of way of defining a set, you are always using another set from where you are considering some elements, and then you see whether those conditions that you specified to define the set are met by that element or not. If no element ultimately turns out to satisfy the condition that you have specified, there is no problem, the set will be empty set, but nevertheless a set. Okay, so we have defined this. Okay, now comes the that part where we see why these SDs behave like what we saw there in that example. Clearly, SD is a subset of this set for each D belonging to T. We already, T is there in the background, that is there in the question statement itself. Also, for any positive integer n satisfying m less than or equal to n, we have GCD of m and n equal to D if and only if GCD of m divided by D comma n divided by T is equal to 1, and where of course D is coming from T. Now this is a property of greatest common divisors, which if we haven't seen so far in this book, I will prove it afterwards. Okay, this is a standard property that GCDs have. You can just simply see this property working, for example, here in this case. This is 2. Now, so that means we see 1/2 of this double implication. This implies that this should be equal to 1, and that is true because 6 divided by 2 is 3 and 10 divided by 2 is 5. So what happens is that the greatest common divisor is the greatest of all common divisors. So if you take that thing out from both of them by dividing by that thing, then there is no other common divisor left other than 1. Okay, so that's why basically it happens. Okay, now what is the consequence of this equivalence? This implies that for any D belonging to T, okay, so we are again writing like what we saw in that example, but exactly how? Exactly how does it follow that this is true from this equivalence? That, however, we won't make a part of this solution itself, but I'm going to show you now. Say you of course have to fix D first. So first you fix D. So now D is any D from T, but it's arbitrarily fixed. Okay. Now if it happens that this M, say you have also chosen an M like that, which belongs to say SD. So that means what? M will be an integer satisfying these inequalities, and GCD of M and N would be equal to D. Now it may happen that M is equal to N. Okay, if M is equal to N, then of course GCD of M and N would be equal to N. So that means our original D should be equal to N. So that is a special case, and in that special case, what do we see? We see that this has to be equal to 1. And why is that? Because if you look at the set Sn, what do you see? You see that the GCD of M and N has to be equal to N, because we have Sn here, and this is possible along with this inequality only in the case when M is equal to N. So that means this set has only one element, which is N itself, and that is why this cardinality is 1. And in this case, of course, trivially this is equal to phi n divided by n. So whatever we are claiming here is true in this special case. And then we have to look at the other elements of SD. So the other elements of SD look like this. The other m's satisfy this inequality. Okay, say you have one such m. Then for that m also, so let me just declutter this space. We can just simply remove the possibility of equality. Okay, so Sn also we have seen, we don't need this. Now we are here. M is strictly less than n, and this is true, right? Then we are saying by this thing that this implies GCD of M divided by D and N divided by D is equal to 1. Okay, now because M is less than N, M divided by D is also strictly less than N divided by D. But you see, you should understand one thing, that because D is the GCD of M and N, so D actually divides both M and N. So this M divided by D and N divided by D are integers, and that is why this thing makes sense. Now we are calculating the GCD of these two things. So M divided by D is, of course, it's a positive integer still, but this is less than N divided by D, and they are relatively prime. So what we see here is that if M belongs to SD, and of course this condition is true, then corresponding to such M, there is a positive integer less than N by D and relatively prime to D. And relatively prime to N by D. The converse is also true. Conversely, if you consider an integer, say k, which is less than N by D and relatively prime to N by D, that is, if you have this, then there would be a corresponding M for which this is true. Can you guess what that M is? It's very easy. We divided by D to get that thing. So now we have to, in going in the other direction, we have to multiply by that. That is KD. There is nothing common other than 1 between K and N divided by D. So if you multiply this thing by D, then that D actually will go inside. That is also one of the properties that GCDs have. So what we have been able to show is that there is a one-to-one correspondence between this set and the set of positive integers which are less than N by D and relatively prime to N by D. So their cardinalities should be equal. Now the cardinality of SD is what it is, and the cardinality of this thing is this. Okay, so that's how we have this thing. If you want, you can make this actually more rigorous by defining that bijection. Okay, then in showing that the function that you define, which you can probably guess from this analysis what the function should be, you will then have to prove that the function is one-to-one and onto. So that will be a bijection. allowing you to write this thing. Okay, but again, the author has chosen not to show these details and he just simply wrote this. We frequently do this kind of thing because the first few times you show that there is a bijection between two sets which you feel like there should be a bijection, then it becomes so obvious and so easy to produce that we suppress that kind of details. Okay, so now we have this thing, but at the same time something else is also true. Note that, or let me write like this, note also that each d belonging to t, well, not each d belonging to t, but rather this, each m belonging to this belongs to at least one SD where D belongs to T and that SD1 intersection SD2 is empty for distinct D1 and D2 in T. Now, how is this again true? You consider any M from here. Now, that M of course has some GCD with N, right? This will be something, and that something, this sum D, of course it divides N because it's the GCD of M and N, so it's the greatest common divisor of M and N, so after all it divides N, and that is why this D belongs to T. And from this equation, from this condition, you can clearly see that this M would then have to be in SD. So for each M there is a D such that M is in SD, and that D of course is just this. And where is this coming from? This is in fact easier. I mean this disjointness. If this were not the case, say this is not empty, you would then have something in this intersection, right? But then by the definitions of these sets, GCD of Y and N should be, on one hand it should be equal to D1 because Y belongs to SD1, on the other hand it should be equal to D2 because Y belongs to SD2, but that contradicts the distinctness of our choice of D1 and D2. Okay, so now we have all the pieces. We can now use them together to draw our conclusion. So we have now partitioned this set into disjoint sets SD for each positive divisor D of N, and we have been able to show that each SD has this size. Thus, taking all the above things into account, we conclude this equation. that n, which is the cardinal, let me show these things in detail, at least here. This is equal to summation of the sizes of SD as D varies over T, and we have already calculated the sizes. These are n divided by D. Okay, now let us go back to that example for once. We noted that this that these things, we interpreted them as phi of some, the given integer divided by one of its divisors. But this is phi of 10, phi of 5, 2 and 1 respectively. So do you see that you can just simply write this equal to, I'm going to do two things here at once, okay. The reason is that here, as your D is varying over T, what you are seeing here is n divided by D, but then n divided by D also varies over T. In the order is opposite. So what I am saying is this, in this particular case, this is our T. So if your D takes these values, then correspondingly your n over D would take these values. The order is reversed. So that means whether you consider n over D or k, it does not matter. Ultimately the sum is the same. Maybe you are rearranging the terms. You are, instead of considering the order phi of 1, phi of 2, etc., you are considering the order phi of 10, phi of 5, the opposite order. In fact, you have the opposite order here. Here you have the usual order. Now, the way we express this fact, and that justifies writing this, is like this. Oh, in fact, I should not have written this final conclusion here itself. I should first write what now I am going to write, the justification for this thing, which allows us to write the final sum like this and then write the final sum. Now, if D varies over T, then so does n divided by T. So what that really means is that as D is varying over T, D is taking on all the values that T has. Correspondingly, n over T would also take all the values in some other order, in fact in the opposite order in this particular case. Thus, n is equal to summation, but because we are not considering, after all we are going to write k, the index will be k, so let's just write k here. So this is simply a rearrangement of the terms of this finite sum. I hope you understand why this is equal to this. We have just simply decided to name this variable k. Instead of calling it d, we are just calling it k, that's all. It's a dummy variable, so nothing will change. And that's how we have the proof. There is another way of proving this completely different from this strategy, which uses the fact that your Euler's phi function is a multiplicative function, and it also uses the fundamental theorem of arithmetic, which says that every positive integer greater than 1 has a unique factorization as product of prime powers. That, however, needs something else, some results about multiplicative functions in general, so I decided not to give that here. Okay, so that's the solution, and in fact let's just end the video here itself. We will see the other solutions to the other exercises in the next Lee update. And tomorrow, of course, again as usual, we are going to see real analysis. Rearrangement of series, I think we have already completed. There is only one exercise, so that we are going to solve tomorrow, and also because that's a very small exercise, and we will start the next section, the root test and the ratio test for absolute convergence of infinite series. Because tomorrow we have infinite series, so I just decided to bring that rearrangement thing here itself, because this is a rearrangement of a finite series, a finite sum. So that being said, this is just all for tonight. If you want to say something, you can of course write in the comment section below, or you can mail me. My mail address will be there in the link will be there in the description. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.